All right. Okay, so this lesson is the squeeze theorem. There's lots of names for it. We'll talk about that a little bit later, but in your Finney text, Finney AP Edition Calculus Graphical Numerical Algebraic text, you will find a little bit on it on page 65. They literally take half a page, I think, for this, they call it the sandwich theorem. So the squeeze theorem, what is it? Well, this is a theorem, just like other theorems in calculus, that if you know sort of the precursors or the necessary conditions for this theorem, you can find, in this case, a limit that's a little bit tricky to find other ways that we've talked about. So evaluating limits has been fairly straightforward so far. You insert the x value in, let's say. If it's a continuous function, then you know what the limit is. If the function is continuous, it's just whatever the x value is, you plug it in. If we have something divided by 0 when you plug in, then you try and manipulate, and if you can simplify the expression or the rational, then plug it in, and there you go, you got your limit. Different things like that. We are going to continue to explore different ways of calculating limits, and this is going to be the next one. So the squeeze theorem says this: if you can identify a function f of x that is always less than or equal to another function g of x, where g of x is always less than or equal to a third function h of x. Am I, oh. Okay, what's going on here? So if we know, so here's the thing, if we know that two of these functions, the one that is the lesser of the least of the three, so it's always kind of underneath a lower y value there, and the largest of the functions, if we know that there is a constant limit or a singular limit as x approaches a certain a value, then because we've set up this inequality here, then we know that the limit of g of x will always be inside those two functions, and so it will share the limit. So let me show you graphically what this looks like, because that might have been a bit of a mouthful or a little bit of a mindful there. So f of x is red. So let's just graph here. I'm going to graph f of x like this. Okay, there's the graph f of x. And g of x is always greater than f of x. So in color is that blue? In blue, I'm going to graph g of x. It's always greater. Okay, there's g of x. And h of x is still always greater yet. And so let me get the green that'll match up with that green on the screen. And h of x is always greater than the other two. Okay, so always greater. Now, if there is a special case, and you can kind of see where we might be focusing our attention here. But if it's possible that we can determine that f of x, the red function, and h of x, the largest function, if they at some point have a common limit, okay, they approach the exact same value, and we have a third function that's always sandwiched or squeezed in between those two, what you can see over here is that at x equals a, we have a common limit for all three functions. So the limit L for the green function and for the red function is identical. And if the blue graph is known to be between those two all the time, you don't have to directly find the limit of the blue function, but what you can do is you can say, okay, as the two functions sort of start to come along here, and at some point, boom, they have the same limit. They touch each other and then diverge again. Well, at that point where they touch each other, if you know that there must be a third function that's in between there, it must have the same limit, identical limit. So again, if f of x and h of x approach the exact same limit at a certain a value, then g of x, the middle function, will also take on that exact same limit. So it gets sandwiched in between. All right? So kind of from a high level, that's what the squeeze theorem says. And you will find that it's not that difficult to try to isolate a function, g of x, to try and create g of x that will be able to we'll be able to find a limit indirectly. So let's move on. So here it is again, and it's also called a few other names, which I think you have in your notes there. So the sandwich theorem in your Finney text, the pinching theorem. I've never heard of the squeeze plate theorem, but apparently there's a squeeze plate theorem. The fly swatter theorem, that's a weird one. I've never seen that one either, but yeah, it's kind of like, fly swatter, I don't know, or you're swatting, maybe you have like a function and the other one kind of comes in like, I don't know. Pancake theorem, I've heard someone say pancake too, like it just pancakes on. But anyways, what were you saying? Yeah, the fly is the middle function. We've got the table, we've got the swatter, and we've got the fly flying. Maybe, yeah. So I don't know. I guess you could call it any one of those. But anyways, we're going to do our first example here. Okay. Just a bit of a side question here. If you look at this, obviously, if you one method that we might try is to insert 0 in right away. I don't know. Is this a continuous function? It looks like there is a restricted value on x equals 0, which happens to be the one we're concerned with. So this is not continuous. You can't just plug a value in because we get cos of infinity, or 1 over 0, which is not good. Okay. Can we simplify this by other methods? Can we simplify this? Well, it's not a rational function that you can factor your numerator and denominator that way and simplify. So we don't have a lot of options here to find this limit, but the squeeze theorem actually can be used. So where do we start with the squeeze theorem? Well, where we start here, we're going to start with, where's my pen? We're going to start with some properties, okay? Some properties of, and we're going to start with the properties of the cos function. So you're going to write this down. Cos of anything, cos of u, okay, we're going to say cos of u, we know is always between -1 and 1. And we know that from the graph. And sine and cos are similar, right? You know that from the graph of sine and cos. So here's the graph of, here's cos. And it always fluctuates between +1 and -1. Now I put u in here because if you have, the cos of any function in here, if it's just straight cos, then this itself has to be, this itself has to be the act as the x. So it could be anything, but as long as there's nothing multiplied or divided or squared or outside of this, then this always is between -1 and 1. So x here, 1 over x, I can simply substitute 1 over x in for u there, and this will hold true. Okay. Now it just might be that x and u are not going to be the same values, but that's okay. We know that the cos function, just a straight cos function, is going to be between -1 and 1. All right? U and x are not the same, but u and 1 over x are the same. All right? So we start off with that. That's great. What we're doing is we're starting to build this function inside here. And what we need to do now is just to multiply by x squared to get this larger function inside. And so with the inequalities, there's some properties that you need to remember, right? You can add or subtract to anything on the ends there, but you have to add and subtract, same thing in the middle. You can multiply, you can divide. Some of the inequality rules, though, if you multiply or divide by a negative value, you have to flip the signs, right? So remembering all those properties, we can still manipulate this. So what I'm going to do is I'm going to multiply by x squared, everything, times x squared. Because that's going to build up to the function I'm looking for in the middle. So this is going to be -x squared is less than or equal to x squared times cos of 1 over x, which is less than or equal to positive x squared. And now, first of all, we have this function that I'm actually trying to find the limit of. That's great. And what's also interesting is that if we evaluate the limits as x approaches 0 for the outside functions, I'll call them, these functions on the end, we are going to get the same value. So let me rewrite this again. So the limit as x approaches 0 of negative x squared should be less than or equal to the limit as x approaches 0 of x squared times cos of 1 over x, which should also be less than or equal to the limit as x approaches 0 of positive x squared. So the properties of limits as well exist and can be applied to inequalities here. And so the valuation of this limit here, this is going to be 0. I'll rewrite this middle part one more time. And if we plug 0 into x squared, we get 0 as well. So here we can see that the squeeze theorem will be able to be applied because the limit of this function on the left and the limit of this function on the right are identical as we approach 0. So that means that this limit will also have to be 0 by definition. So by the squeeze theorem, the limit as x approaches 0 of x squared cos of 1 over x equals 0. So if we graph these functions, there's our positive x squared in red, negative x squared in blue, and the green is the x squared cos 1 over x. So if you zoom in, kind of cool, you can kind of see that it stays in between the whole time because we've built it that way, right? We've built it that way. And so because the two outside functions, or the upper and the lower function, converge to a single limit, then the inside function, although we can't see it, obviously that's going to squeeze in there as well. Okay. All right, and here it is right here. So this is the work for that that problem. Any questions?
Wait, how exactly would we know times -1? Like, do we just do it because we know what cos has to be?
Yeah. So if you look at this right here, you know that cos has a range, right? And so whenever you see sine or cos, those are going to be the good functions to start with in your kind of like your proof here of this, in your working out of this theorem. So cos of anything has to fluctuate between -1 and +1. So that's a good place to start. You know that this is going to be between -1 and 1. And then in order to start to build the function in question, you work the properties of inequalities and you either multiply, add, or divide. So we're gonna do some more examples where you can see, but basically you build up to the function in the middle, and then if you have common limits on either two ends, then you can use squeeze theorem to identify the limit. All right. Okay, we are going to do some more examples, but let's just talk about some takeaways here so far of the lesson. So this is called the squeeze theorem, which helps us to remember what this theorem is all about. This little note here is that when theorems are named after mathematicians, it's a little tough to remember what the theorem is or how it works, right? Euler's method, which we haven't talked about quite yet, but it's like, well, what is that again? Newton's method of linear approximation. Okay, well, linear approximation I remember, but if it was just Newton's method, I'd be like, what? So squeeze theorem helps us to remember what the theorem actually does. So remember, it squeezes a function between two easier functions to work with, or two other known functions. Known minimums and maximums can be really handy too. That you know what the maximum of, for example, -x squared is, you know what the minimum of positive x squared is, and if they're the same, then that's handy to know. Okay. All right. So this question right here is in your notes as well, and it says this: the function f of x equals cos of 1 over x times sine of x cubed minus 1 over x to the fourth is bounded from below by g of x equals this function right here, And it's also stated that it's bound from above by this function right here on the interval -1 to 1. The question here is there enough information to determine the actual limit of this function as x approaches 0? Okay, as x approaches 0. So we know that the functions are bounded. And so we know that there's one function, that kind of looks something like this maybe, another function that looks something like this maybe. Do we have a common limit, or do they just come close to each other? That's what we're looking for. So how do we work that? Well, let's just take a look at it. So what it's saying is that on the bottom, g of x would be -√1.11 minus x squared. And that is bounded by, or less than, our cos of 1 over x sine x cubed minus 1 over x to the 4th. Great. Which we know is bounded, again, by the upper function of positive √1.11 minus x squared. Okay, so we know that that's true. The question is there enough information to say that this limit would exist, and what is it? Okay, so notice that this is x approaches 0. And you will get a question like this perhaps on the AP exam saying, hey, does the squeeze theorem apply here? Does the squeeze theorem apply? And again, what you'd have to do is you'd have to find out what is the limit of the lower function and the upper function, and are they identical anywhere, and are they identical at the point in question? So in this case, what we do is we simply look at x approaches 0, and we are going to plug 0 in to here and here and find out what these values are. So this is going to give us -√1.11. This one's going to be positive √1.11, isn't it? So that's what happens when we put 0 in. So we know that this function is somewhere in between. But I guess the question is this enough information? So what do we have to have happen? This limit has to equal this limit. And clearly those are not the same. You see that? So what we can surmise here is, where's my answer question? Give me a second. I think it's over here on the next page. It is right here. Okay. So yeah, we have on the left a -√1.11 and on the right a positive √1.11. But because those are not the same values, so here would be positive √1.11 maybe up here and negative down here, we can't really say that the limit of this function is a certain value. We just know that it must be in between these two values. Okay, so unfortunately, in this case, we don't have enough information. It turns out that the limit doesn't exist, but the given information didn't tell us that either. It only told us we can't use the squeeze theorem with these bounding functions to determine if it does exist. So your answer, please summarize that in your notes, that because, as I mentioned, these numbers right here and right here, because they are not identical, you don't know if there is a limit at all. So not enough information. So just remember that what the squeeze theorem does is it identifies a limit if the two bounding functions have a common limit. So they have to have the same limit on either end. Okay? Known bounding functions are handy, but they are not definitive if the limits are not identical. Okay? All right, before we get to some more practice problems, I want to show you this. This is one of the common squeeze theorem sort of examples and problems, but do you recognize this right here? We took a look at this in Calc 30. This is a famous limit, a limit as x approaches 0 of sine x over x. Do you remember that? Yeah. Do you remember offhand what that is?
No, 1.
Is it 0 or 1?
It's 1.
Okay, I think it's 1. All right, we're going to use the squeeze theorem and some given information here to show what this limit is. So the traditional proof uses some really neat areas in trigonometry and the unit circle to show that sine of x is less than x, which is less than tan of x, and cos of x is less than or equal to sine of x over x for any values between negative pi over 2 and positive pi over 2. So we can use this information to find this limit of sine x over x as x approaches 0. So we're going to have to take pieces of the given information and sort of like creatively create sort of h of x and sort of f of x and h of x. But let me just show you how we might go about this. So the first one, this sine of x is less than x, less than tan x. Okay. If we divide everything by x here, what I can see is that at least part of this double inequality here, that I actually have this right here, that sine of x over x is less than or equal to what? 1. Yeah. Yeah. So I know that in part. I'm not really too concerned about the tan x part, to be honest. The second bit of information that we're given is that cos of x is always less than sine x over x. Well, if that's the case, then I can make a double inequality from that piece of information too, and I can write this. You see that? Okay. Everybody good with that? So I've made now a double inequality from these two. And if I now take the limit of this right here, I really don't have to do anything else to it. But if I take the limit as x approaches 0 of all of these three, then what do I get? Well, what's the limit as x approaches 0 of cos?
1.
That's 1, which has to be less than or equal to this particular limit, which has to be less than or equal to, well, what's the limit as x approaches 0 of just 1? So that's just 1. Yeah, x doesn't affect that. So guess what? I have a lower limit and an upper limit that are identical, so the middle limit has to be the same. So there you go. You can prove by the squeeze theorem, or show, using the squeeze theorem and this given information there, that we have this limit is equal to 1. And yes, you remembered correctly from before.
Like, this is going to be insane on the test, like trying to understand like which theorem's which.
I mean, you're going to have to be attentive on the test when you, to remember which theorem is which. Some of the questions will say use the squeeze theorem to show that. But some of them won't. Some of them will just say determine this limit using calculus methods of some sort. So there's a rule coming up that we haven't studied yet, L'Hopital's rule. And maybe you can use squeeze theorem. Maybe use direct substitution. Maybe. So however you can do it, you just have to kind of show. And then you might have to state, by squeeze theorem, this is the limit. Or using L'Hopital's rule, this is the limit, whatever. Okay, let's get to this, the question here. You have a handout here with some questions on it, so let's change gears a bit. Let's do some AP style questions here. So this first one, let's call this question number 1. It says, the function f is defined for all x in the interval 4 to 6. So x is between 4 and 6. Which of the following statements is true, or if true, implies that the limit of f of x as x approaches 5 is 17? Okay, so we're assuming this is going to be true, that f of x approaches 17 as x approaches 5 right in the middle of this. Okay? So let's read through these carefully. There exists a function g with f of x is less than g for in this interval that has a limit as x approaches 5 of 17. Okay? So this is talking about f of x. This is saying there's a g of x that is greater than f of x all the time, and it's 17. Okay, well, let's think about this. Let's think about the next one. There exists a function g with g of x is less than f of x, where g of x approaches 5 is 17. Okay. Okay, for both of these two, we just have kind of one other function we're referring to, like one that there's an upper function, b that there's a lower function. I'm looking at c here, and I'm seeing there's 3 different functions mentioned here. This is looking rather sandwichy, if that's a word. Can we make that a word? Sandwichy? Squeezy? let's see, there exists a function g and h with f of x being less than g of x being less than h of x on this interval, where the limit of g of x approaches, as x approaches 5, is equal to the limit of h of x as x approaches 5, which both equals 17. Okay, so we might be getting a little bit closer here, hey? F of x. So is f of x, this is the one in question, does that make sense here? Well, g of x and h of x are both 17, but f of x is underneath that. This is not squeeze theorem, it's close though. Let's look at D. There exists a function where f of x is in the middle of g of x and h of x, and the limit of g of x and h of x as they both approach 5 is both 17. So does this look rather squeezy? This looks pretty squeezy to me. Those both approach 17, and so f of x is let in the middle of it. So would you agree with me that D is our correct answer? Okay, I like D. I like D. Any questions about that? Okay, let's move on to the next one. Okay, so kind of question number 2 here. So the function g is given by this, 7x minus 26 over x minus 5. That's g of x. H is given as this one right here. Okay, so we got g and we got h. And f is a function that satisfies this, this hypothesis here, that f of x is between g of x and h of x for all x values from 0 to 5. What is this limit as x approaches 2? Well, I guess what we want to look at and say that f of x is the sandwiched function here. So if I find out what the limit of g of x is and the limit of h of x is as x approaches 2, then if they're the same, then the limit of f of x as x approaches 2 must be that way. So I would write it out like this, and you may be already ahead of me, but let's do the limit as x approaches 2 of 7x minus 26 over x minus 5. That would have to be less than or equal to the f of x in question, which would have to be less than or equal to the limit as x approaches 2 of the upper function, which is 3x plus 14 over 2x plus 1. So we've got this set up. Looks pretty squeezy to me. So let's plug in x equals 2. And I've got 14 minus 26 is what? Negative, is that 12? Negative 12 over negative 3. That's equal to f of x. And 2, so what is this? 12 plus 14 is, what's that, 26 over, oh, I have to double check my mental math here. You guys uncovering anything here? 6 plus 4, oh, 6 plus 14. 20 over 5. And is this one correct or no? Did I do that right? 14 minus 26. Okay, so are these limits over here, are they the same?
Yes.
Okay, so 12 over 3 and 20 over 5, that's going to be positive 4 and positive 4. Nice. So what can be said? The limit is 4. Do you like B there? You love it. Well, that's good to hear. I'm sure B loves you back.
You like me so much, why don't you marry it?
Classic. Classic. You gonna marry B?
That seriously just offended me, Thomas.
So that's the first time you've ever heard that joke, probably. Okay, let's take a look at this right here. Let f be the function of x, or a function of x. The value of limit of f of x as x approaches a can be found using the squeeze theorem, g and h. Which of the following graphs could be graphs of f, g, and h? So the squeeze theorem applies to f of x. Which ones could be f, g, and x of these 4?
That's a B, doesn't it?
All right. So you're saying D. Okay. Why did you say D?
Because in B, the F goes back up, and H always has to be on top, like greater than, and then F always has to be in between, and then G always has to be on the bottom.
Good. I would agree. H of x is always on top here. G of x is always underneath. and f of x is always in between, and they do converge at a single limit here at a. The problem with this one, obviously, f of x is above h of x, then it's below all of them, and then it goes crazy. This one, it's always in between, but they do not converge to the same limit as x approaches a, right? And over here, f of x, if you follow this carefully, it does kind of pop up above both of them on the other side. So yes, D is the correct answer. Love it. Love it. Okay. So there are two questions that I am going to leave with you to try and do, and I don't have them on my screen, but I am going to write them down here.
Done one already?
Sorry? Yeah, you did one. I want you to do it from scratch again.
Well, I mean,
See if you can do it without
slightly
looking.
different.
Is it slightly different?
It's 1 over x squared instead of 1
Oh yeah, so it's not the same, but it's very very similar.
I just did it the exact same.
It matters.
Okay, use squeeze theorem to find.
It matters.
Okay,
Stupid.
limit as x approaches 0 of x squared cos of 1 over x squared. And b over here, the limit as x approaches infinity. You have to remember about infinite limits and some properties there. 2 minus cos x over x plus 3. All right, so I'll let you work on those, and that kind of wraps up our squeeze theorem lesson. Any questions at all? Yep.
Not related to this. Could I just do worksheets? Or
Can I say hi?
All right, so here's the answers to these questions. Hope you paused the video and tried to try this on your own. But what you want to start with, just like our example previous in the lesson, you want to start with cos of u, or cos of 1 over x squared, whatever that is in there, has to fall between -1 and 1. That's our first line of explanation there. Multiply by x squared, you get line 2. Take the limits of those, you get line 3, very similar to our example. And if you plug in 0 in for x, you get 0 is less than this limit, which is also less than 0. Because 0 is the limit on the lower function and the upper function, we have squeeze theorem applied, so the limit of this function is 0. Now, same thing happens on the other side, slightly different. There's a little wrinkle here. You want to start with the cos function as well, between -1 and 1. Now, if you think about the graph of the cos function, okay, the graph of the cos function starts at 1, goes to -1, back up to 1. But the negative value of the cos function starts at -1, goes up to +1, down to -1. So the range is still the same. So negative cos is still between -1 and 1, no problem. Now we add 2 to this double inequality, and -1 plus 2 is 1. You have now a 2 in there, minus cos x, and you have less than 3. We can divide by x plus 3, or multiply by 1 over x plus 3. And because x is approaching positive infinity, then this is going to be a positive value, so you don't have to be aware that this might be negative. It's going to be positive. And so we have this line right here, and we finally now have the function built in the middle. And if you apply limits do exist for the end functions, the upper and lower, and they both equal 0 as well. Why? Because remember this one, the limit as x approaches infinity of 1 over x, that equals 0. So this would be the case in both of these here. So we see that the upper limit and the lower limit are identical, and that's what the middle limit would equal then too. So this one equals 0 as well. Okay, so that's the lesson on the squeeze theorem. I hope that helps, and there you go. There's your squeeze theorem.